Great. So I just want to quickly show where we are in the prescribed textbook, and then I'm going to do a small example after that in terms of a practical problem to try and solidify what we've learned so far. So we're almost done in terms of what we need to do. The only thing that's still really that we need to look at is the surface tractions and make sure we can relate that to the strain, to the stress tensor. So that is essentially what's left. And then after that, motivation for why it's important that we all of a sudden go for this kind of theory. So essentially, where we are now, we've looked in the last videos, we've looked at stresses and equilibrium. So we've got a good understanding of what's going on there. So let's just quickly look at the prescribed textbook, what we've learned so far. So there's the capital U. This is now the displacement field, which has got a U, V, and W field. So each one is a function of X, Y, and Z there. So this is, the textbook just writes it then as a capital U. So not to be confused with this U here, which is the displacement in X direction, displacement in Y, and displacement in Z direction. This essentially what we've got is the body forces, as we've discussed. Here are the surface tractions. We'll still talk about them. So they've got units Newton per meter squared, so pascals. So we'll talk about them. Here are point loads that we've got. This is that potato that we looked at. And after we derive sort of the equilibrium equations, here's just the equilibrium equations now in the three-dimensional case. So what we had is, we had sort of these two terms, essentially these four terms. And those terms were sort of omitted because we didn't consider the Z case in our derivation, but it's trivial to do, and you can follow the derivation now quite properly and quite easily in the textbook. So the point is just, this is the full equation. So we've got three equations where we essentially have the sigma xx as derivative of x. So on the diagonal here, sigma yy on the derivative of y in the second equation, sigma zz with respect to the z variable in this third equation. And then we have sort of the shear contributions. And as what we've seen is essentially if there's a normal variation in a normal stress over a domain, then there needs to be some shear stress to try and counter that. And there's the body forces that's acting in. So this is sort of the equation. This will look very familiar now after you've watched the last videos. Here's that Voigt notation that we discussed. You can now clearly see this symmetry that we have now enforced by having a symmetric strain tensor, but we made a 6x1 vector, and if we map that sort of towards a stressed vector, that's a 6x1 stress vector, and that mapping is enforcing symmetry of, it implies that we don't have a material with local couples. So that is essentially the implication of that. One thing that I'll talk about later is just why all of a sudden we have to go for this kind of a description for stresses. Why isn't something like forces sufficient? But we'll get to that at some point. And then after I've done the example problem, I'll continue on to link the stress to tractions, and just to make sure that we can relate that back. And these tractions are in essence then acting on those surfaces there. And then once we're done with that, we're in a good place in terms of rolling out now the whole solid mechanics boundary value problem that we need to solve. And what I'll show you is essentially for that problem, that to solve that problem in general, we need to solve 15 variables with 15 equations. So that's what we're going to be heading towards. Okay, so I just want to make sure everybody's on board where we're going. Here's just the strain displacement relation. So I've done this all in reverse, because I've driven the problem from the displacements, strains, mapping strains to stresses, stress equilibrium. So the textbook is just doing it in reverse. But here you can see the Voigt notation for the strain vector, and then the stress-strain relations what we derived now. So this is just the classical Hookean kind of relationships that we have, so the generalized Hookean relationships, and then we end up with sort of the inverse of that if you want to map now from strain to stress. Okay, so all of this is now very nice and familiar. After I've done an example problem, I'll talk about plane stress and plane strain at some point as well. But this is something that I think you've covered quite extensively in MOW 227 as well as in MSY 310, but I'll just recap that. And essentially, plane stress are sort of very thin kind of bodies, and then everything, loading, etc., is within that plane. And then the plane strain problem is essentially a problem where we have sort of a very thick kind of cylinder, and we're taking a slice out, but this is sort of infinitely thick in that dimension, and we're taking a slice out and then asking what's happening in that plane. And so this thing struggles to contract in this direction because of all this mass on the sides. So essentially plane strain means all strain is in the plane. Plane stress means all stress is in the plane because it can contract out of the plane. So, but we'll go through that and discuss that. But that will hopefully make sure that we can follow where we are. So we essentially now sort of page 24 of the textbook. The only thing that's now missing is really just to relate the stress to the tractions. Okay, and do a sort of an example problem. But what I'm going to do now is I'm going to switch this video off and I'm going to continue on the whiteboard, start a new video where we can now tackle an example problem and make sure that we get comfortable with what's going on in the example problem. Okay.